Okay, so today we're going to talk about matter and energy. And so you can see in this picture, what I've done is I've included a diagram of the Earth's energy budget and where we get our energy from. Obviously, we get our energy from the sun, and what's happening to that energy is what you see in this diagram. Now, in this presentation, we're going to talk about what that energy does to matter, what energy does to matter. So, first question here, it says, how would you explain the movement of the particles in the water and food coloring? So we did this during our Zoom meeting. We looked at the water and food coloring. You also saw the video for the introductory lesson. So one thing that you want to consider is gas and liquid particles are constantly in motion. They're constantly in motion. So what could you tell me about the movement of the particles in the red cup versus the blue cup? If I told you that both of those solutions were water and both of those things that were added were food coloring. So the solutions weren't necessarily made of different things. What can you tell me about the movement of those particles? Go ahead and answer that in your Pear Deck. So when you answer that, what you maybe didn't even think about is this idea of diffusion. So those particles of the food coloring, they are diffusing. They are moving through. They're moving from areas of high concentration to low concentration. So particles are going to constantly move until they have moved throughout, say, for example, an entire room. Okay, that would be an example of diffusion. Effusion is a process in which gas particles pass through openings. And the most apparent example of this is like the last time you had a birthday and you had helium balloons for your birthday party. Well, eventually that helium kind of effuses out. It leaks out. We say it leaks out. Really, what it's doing is all of the helium particles are moving out of the balloon and into the atmosphere around you. So things are going to effuse at a faster rate if they have a lower molar mass. And that comes from the equation for kinetic energy, which you see right here. Kinetic energy is 1/2 mass times the velocity squared. So here I've included a derivation of Graham's law of effusion or of kinetic energy, which gives you Graham's law of effusion. But basically what this says is that particles that have the smaller molar mass are going to effuse faster. So let's talk about energy. You just saw on the last slide, and there is a question on this slide. Energy. What is energy? Energy is the ability to do work. Okay. Energy can be transferred from one form to another. So kinetic energy is the energy of motion. So when I'm thinking about kinetic energy, 1/2 mv squared, I'm thinking about running down the street. How many of you are runners? We've got a lot of runners in chemistry this quarter. So if you're thinking about how fast are you moving around that track, or how fast are you moving in your race that you're running, that's going to be your kinetic energy or energy of motion. Think about cars moving down the road. That's kinetic energy. You see kinetic energy and potential energy every single day. Potential energy is something that affects you constantly. I mean, go ahead and, slip yourself off of the chair that you're sitting in right now. That would be potential energy. You had potential energy, you have this gravitational potential energy, and hey, guess what? You ended up falling down on the floor because your gravitational potential energy is due to your position. Your mass times gravity, the effect of gravity, times the height at which you're falling from. So that is going to be your gravitational potential energy. We also have elastic potential energy. Think bouncy balls or poppers. I mean, there are so many things. And next year, if you're looking into taking physics, we really dive into this idea of kinetic energy and potential energy. So what I'd like for you to do is I'd like for you to give one specific example where you've witnessed kinetic energy and where you have witnessed potential energy. So in these next 3 videos or 3 slides, there are going to be videos, and I would like for you to answer those questions. You can go ahead and pause this screencast if you would like to, and then come back to me after you are finished answering the questions. There were 3 slides with questions. So then we're going to talk about temperature versus heat. And hopefully you've watched the videos now, so you kind of have a better idea of the difference between temperature and heat. The degree of hotness, how hot something is temperature. And temperature depends on the particle speed. Temperature is a measure of the average kinetic energy of the particles. Again, Temperature is a measure of the average kinetic energy of the particles. It depends on particle speed. So the faster the particles are going, the higher the temperature is going to be measured. Now, the quantity of hotness is your heat. That depends on the particle speed and the mass. That's your kinetic energy. So I apologize. I think I just said that temperature is your kinetic energy. Temperature, it goes into the average kinetic energy of the particles, but really it's based on how fast the particles are moving. Whereas the heat, the hotness, is how fast the particles are moving and how much mass they have. And I think that the examples that were given in the videos that you watched are actually really good examples. So if you happen to skip the videos, I would definitely go back and watch those videos. Okay. And when I'm measuring heat in joules or kilojoules. When I'm measuring temperature in Kelvin or degrees Celsius. So again, temperature measures the average energy of the particles or the average motion, and heat is a measure of the energy transferred. So heat measures the transfer of energy. Energy is transferred in three different ways. It can be transferred through heating, it can be transferred through working, and it can be transferred through radiating. The radiating is easy because it's the sun. Working, I think about like the pistons in your car. So the pistons go down, they push down, and they're increasing this pressure. And so then all of a sudden they're increasing the pressure and the volume is going down. And so that's what's causing the increase in pressure. And now all of a sudden you've got this big buildup of pressure. And now that pressure is going to do work on the piston. So the piston's going to push down on the chamber and then is going to do work on the chamber. And then the chamber is going to do work on the piston. Okay. So that's going to be your three transfers of energy. We have heating, working. Working is a measure in pressure and volume changes, and radiating, which is what you get from the sun. Okay. Heating is measured in we'll learn in mass, a specific quantity, and how much your temperature changes. So temperature, a little bit of a review in temperature, and we covered this in our last unit, but I want to make sure that I really discuss it, okay? So our temperature it's measured in Kelvin is what we're going to use it mostly. We're going to use Kelvin and we're going to use degrees Celsius. So degrees Celsius plus 273 is Kelvin. Absolute zero is the lowest temperature you can possibly go. Absolute zero is 0 Kelvin. There is nothing negative in the Kelvin scale. So 0 Kelvin is the lowest you can go. It's the absolute lowest. And at that point, theoretically, all motion stops and all volume becomes 0. So 0 Kelvin is negative 273 degrees Celsius. And I'll state again, there are no negative numbers in Kelvin, but there are negative numbers in degrees Celsius. So here's a question I have for you. And this is an important question. I didn't put a Pear Deck question stopper here, but it's really important because it's going to show up on a test. If a sample of copper or anything is heated from 20 degrees to 50 degrees Celsius, you're going from 20 degrees Celsius to 50 degrees Celsius. How much does that change the temperature in Kelvin? Well, as you go up by 1 degree Celsius, you're also going up by 1 Kelvin. So really, you're going up from 293 Kelvin to 323 Kelvin. And the difference there is 30. So you're changing by 30 degrees Celsius, you're changing by 30 Kelvin. So when we're looking at the properties of matter, when we're going to look at the properties of matter, our properties of matter are going to be, we're going to look at solids, liquids, and gases. Solids have a definite volume and they're not fluid because those particles are super close together. So take your hands and make a fist. Okay, I'm doing it right now. You just can't see me. Take your hands, make a fist, and just start vibrating them. And they're just vibrating. Now, as soon as those vibrations are overcome, and as soon as you start moving your fist around, now all of a sudden those particles have now turned into the liquid phase. So that matter going from vibrations to movement causes it to go into the liquid. So vibrations only is solids, and then movement is liquids. And I love the Eureka videos because I think that they're really detailed. So I would go ahead and click on this link right here, and it's going to take you to another video. Now, some things about solids. Solids aren't easily compressible. There's not very much space between them. And so, I mean, there is a little bit of space between them, but they're in these fixed vibration. They're kind of restricted in their motion. And so they're not easily pushed together. When the vibrations are greater than those forces holding them together, now all of a sudden the solid has melted. So again, you've got these forces of attraction right there. And as soon as you put enough energy in to get rid of those forces of attraction, now all of a sudden your solid is melting. Now, solids have a definite shape. You have crystalline structure for some solids, and that's a three-dimensional structure showing the arrangement of the particles. An amorphous solid has no ordered structure. Okay, glass is a good example of an amorphous solid. They actually have to put a coating on your glass in your car so that, like for your windshield, so that when it shatters, when it breaks, it will hopefully break in specific patterns. Another thing, like if you see like stunts in movies and you see the glass shatters into these perfect cubes, it's because they're jumping through walls of sugar. It's kind of cool. So solids tend to have a higher density. Why do you think that they have a higher density than liquids? Well, let's think about this. Density is mass divided by volume. So if we're not changing our mass at any point, but we are changing our volume, meaning the space between them. So the solid particles close together, as they get farther away, they're turning into liquids. So greater volume, and so then you have a lower density. So solids have a higher density than our liquids. Properties of liquids. So liquids, once that motion starts, that motion's moving, but the particles are still relatively close together. So liquids have a definite volume, but they will take the shape of a container. That's the indefinite shape. So if you take a water bottle and you pour that water from the water bottle into a bowl, it has changed shape, but you have not changed the volume that is there. Now, how is that different from solids? Solids have a fixed shape and a fixed volume. So liquids still have a little bit of space or have space between them, but not too much. So they're relatively incompressible. However, very interesting note, your oil that you put in your car is based on compressibility. Your W rating is based on the compressibility of those liquids. Liquids also have a relatively high density. Now, comparatively speaking to solids have a higher density than liquids, but then gases have a very low density. Okay. Now, liquids are fluid. Now, when I say fluid, I don't mean that I'm talking about liquid necessarily. I just mean fluid, meaning that they're free to move. Fluid means free to move or will diffuse easily. Liquids can also have a high surface tension. So water has really high surface tension. And that's why when you go out in the morning and you see these beads on grass or on a freshly waxed car, that's because of the high surface tension. Okay. Or if you pour water into a bowl and you see a bubble up, again, high surface tension. Also, a liquid is going to boil when the vapor pressure is equal to the external pressure. So when you're boiling water, think about it. What is filling those bubbles? What is filling those bubbles? What are you doing? You're taking liquid water and you're turning it into gaseous water. So that gas is trying to escape from the water. And all of a sudden, as soon as that gas inside of the bubble is able to escape, it pops out and escapes the liquid. But what is it that's escaping? It's water vapor that is escaping. So you have H2O gas is in those bubbles of the water that you're boiling on the stove. A lot of people will often put on tests, they'll put H2 plus O2. It's not, you're not doing a chemical change, you're doing a phase change. So in those bubbles, you're going to have water vapor. Why does water boil at a lower temperature in the mountains? Well, think about it. Low temperature in the mountains. Well, it's because as you go up into the mountains, you actually drop in pressure. So you have less pressure on the outside pushing on those bubbles. So you've got less pressure pushing out. So as that water wants to escape, the water vapor wants to escape, it's easier for it to escape because it doesn't have someone pushing down on it. Have you ever had a kid or a baby brother or sister jump on you? And when they're jumping on you and pushing you down, it's a lot harder to get up, right? So if they're not applying very much pressure on you, it's a lot easier to get up. So up in the mountains, you have a lot less pressure. And so therefore, the water vapor is able to escape because it's not being pushed down by the atmosphere around it. So go ahead and make sure that you've answered this slide before you move on. Properties of gases. Now, gases have this ability to expand. Those gases, gas particles, are so far apart relative to their size. They're moving and grooving. They're moving all over this room that I'm in right now. There's gas all around you, but it's moving super fast. Now, notice I said gases are fluid, which again means free to move. Gases are free to move. They are they have a low density. Why? Greater volume, much more space between the particles. They're compressible. Why? Much more space between the particles. There's more space to push them in. They diffuse and effuse very easily. And there are fewer forces of attraction between the gas particles than there are within liquid particles or solid particles. Now, gas pressure. This is how we measure gases. We measure gases in pressure. Pressure is the force exerted by a gas per unit surface area. So why is there no pressure in a vacuum? Well, think about it. In a vacuum has no particles. If there's no particles, then there's no force being able to be exerted by the gas. Atmospheric pressure is the collision of the molecules in the air around us. And we measure pressure in kilopascals, mmHg, which is millimeters of mercury, ATM, which is atmosphere, or torricelli. So our SI unit for pressure is kilopascals. But we are, like, if we're at sea level, we're at 1 ATM. 1 ATM is the equivalent of 101.3 kilopascals and 760 millimeters of mercury. And you measure this pressure with a barometer. We're going to spend more time discussing pressure next week when we reconvene. So phase changes. When, and this is something that we're going to spend a lot of time on tomorrow in our next classes, when you have a matter go from solid to a liquid to a gas. Solid to a liquid would be melting. Liquid to a gas would be evaporation. Now, if I'm going the opposite way, gas to a liquid, that's condensation. Liquid to a solid, that's freezing. I really like this video on evaporation. So I've put evaporation right here, and there's a link right here to a video I would like for you to watch. Now, it takes a certain amount of energy or releases a certain amount of energy for that phase to change. And that amount of energy that's required or released is this delta H, this change in heat for vaporization, or change in heat for condensation, change in heat for solidification, for freezing, and change in heat for fusion. So when we're talking about melting, we're talking about the heat of fusion. Now, as phase changes, what happens to volume? Going from solid to a liquid to a gas, particles are getting farther apart. So your density is going from larger to smaller. When you're going from a liquid to a solid, your particles are getting closer. You're getting more dense because you're getting a smaller volume. So now you'll see sublimation. Sublimation, you have experience with sublimation, I promise. Have you ever had a piece of dry ice or seen a piece of dry ice? Bam. Sublimation. That's what sublimation is. Because notice, what dry ice is frozen carbon dioxide. And carbon dioxide does not want to be frozen outside, like in the regular atmosphere. So when that dry ice is taken out of the freezer, it goes directly, bam, from solid to a gas, just right away. And it does that because it's not comfortable in the pressure and temperature conditions that it's in. So that those particles want to be a gas. It's the same thing. Liquid nitrogen is not sublimation because it's really just evaporation, but liquid nitrogen is like that too. Nitrogen wants to be a gas at room temperature. So if you have liquid nitrogen and you escape it, you release it into the atmosphere, it's going to turn into a gas. So if you've ever gone to any of those ice cream places that use liquid nitrogen to freeze, that's part of that process. And we'll talk about that tomorrow a little bit. But sublimation is when something goes directly from a solid to a gas and it does not form a liquid. Please do not misunderstand me. I am not saying liquid nitrogen going to a gas is sublimation. I did not say that, and I didn't mean for you to get confused. Sublimation is when solid goes to a gas. So for example, dry ice, solid goes directly to a gas. Okay, think about the band Sublime. Okay. Now, For these questions, I would like for you to draw, what do you think the zoomed in, the very close, the microscopic level, what do you think the particles look like for a solid, for a liquid, and for a gas? Go ahead and do that. And then in 1 minute, write the most important thing that you learned from today's lesson. And that's it for us for today. Thank you.